Okay, in this screencast we're going to introduce a new topic of measurement, and we're going to go through some aspects of area and surface area involving some 3D objects. But initially we're going to look at just some straightforward areas, but before we do some area conversions, so some units of area conversions. So units of area conversions. I'll show you what I mean in a moment, because this can be a bit tricky. Units of area conversions. So if I said to you, what does in 1 meter gives me in centimeters? Well, I guess we all know it's 100 centimeters. But what about 1 meter squared? How many centimeters squared is that? Now, if you answer 100, you're in good company, and that a lot of people will here, but you're also in good company in being wrong. 1 meter squared is not 100 centimeters squared. Give this a little thought, and it's always good in these situations with all these conversions. I'd encourage you just to draw a little square and say, well, all right, 1 meter by 1 meter, that's my 1 meter squared. All right, but if I want it in centimeters squared, so what's a meter in centimeters squared? So I'll change that to 100 centimeters by 100 centimeters. That's still 1 meter by 1 meter, which gives me the meter squared. But now, in centimeters squared, it's 100 times 100, isn't it? 100 squared centimeters squared, or 10,000 centimeters squared. So 1 meter squared is actually 10,000 centimeters squared. And similarly, we could go 1 kilometer is 1,000 meters, but 1 kilometer squared is going to be 1,000 meters by 1,000 meters, or 1,000 squared, or 1,000, which is 1,000,000 meters squared. So a kilometer squared is 1,000,000 meters squared. And then finally, shall we have a look at 1 centimeter is 10 millimeters. 1 centimeter squared is 10 by 10, or 100 millimeters squared. Okay, so the units of area and the conversions between them is a fairly important concept. All right, as is finding the area of some pretty basic shapes. So if we just now look at area, I'm going to race through some old news, really, some recap of area. Right, if we've got a square, right, then it's just going to be, if this is my side x, then our area is simply going to be x squared, isn't it? Now if I've got a rectangle, now we've got x and y, and my area is just xy. Now if we've got a triangle, I'm racing through this stuff because I know you know it. Now if I've got a height there and a base there, then my area will be 1/2 times base height. What else do we know? Okay, what about a rhombus, which is a square that's been sort of given a bit of the slant treatment? So it's like that. What we need to know with a rhombus is what the length of the diagonals are. And once we know what that is, so they're x and y, so x all the way down there, y all the way down there, our area is xy. Apologies for the rough diagram. Now for just a parallelogram, so we're looking now at a rhombus has to have all sides equal. Parallelogram is like the rectangle. It doesn't have to have all sides equal. And here, say that we've got our height and our base, and our area is simply base times height. Okay, what about this guy here, our friend the trapezium, where we've got one pair of parallel sides? It's called a trapezium. We might have sides A and B, the parallel sides A and B, make them parallel with little arrows there. We've got a height, and our area is 1/2 height by the sum of A plus B. That's our trapezium area. Now what about a kite? So we've got, kite's got these adjacent sides that are equal like this. adjacent sides are equal like this. Again, with the kite, bit like a rhombus, we want the diagonals. If we know what the diagonals are, if that's x and that's y, then our area for our kite, is a half xy, as it is for the rhombus. And I've just noticed an error here. Our rhombus area is 1/2 by those diagonals. I apologise for that one. Alright, let's keep going. What about our friend the circle? Area of a circle. Let's have a little from the centre. That's our radius, and our area is pi r squared, is it not? And let's just have a look at the sector of a circle then. So this is just a piece of the circle, like so. If this is my angle theta, then my area is going to be, and this is r here, it's going to be theta over 360, because that's the fraction of the circle I've got, times pi r squared, being the whole circle's area. Okay, let's now look at, now that's gonna lead you into exercise 6c, which is some work on just the area of two-dimensional shapes. Now, if we go to prisms and cylinders, so now we're going to look at the surface area of prisms and cylinders. So what we're looking to do here is take a three-dimensional shape and make some calculations as to the surface, the area of the surface. Okay, I've just drawn out some prisms here. Now we recognize a prism because prisms have what we call uniform cross sections, which just means that if we take cross sections, that means it's putting a slice through our three dimensions. You can imagine chopping them. Then the cross sections, which are these faces that result, are uniform. They're the same. It's got two identical congruent ends. That's what our prisms look like, as opposed to our pyramids, which have a base but then triangular side faces leading to a point. Here we've got uniformity through the cross section and two congruent ends. I might just make that point. Okay, I've just made that point about prisms and what defines them: uniform cross sections and two congruent ends. So we've got our and defined by those ends that we're talking about here, these congruent ends, that those shapes define what sort of prism we have. So here we've got triangular ends, so it's a triangular prism. Here we've got rectangular ends, so this is a rectangular prism. And this guy here, circular ends, circular prism or cylinder. So let's write that out again. Triangular. Okay, so our job is in finding the surface area is just simply to find the individual areas and add them together. Now, often we've got pairs of sides that are equal in area. By definition, our ends of our prism have to have the same area because they are congruent, they're identical. And then we've got all these parallelograms. So we've got 1, 2, 3, 4, 5 sides, faces. What we need to do is find the areas of each of those and add them together. The surface area, the total surface area. Over here in the rectangular prism, we've got actually 3 pairs of identical rectangles. Once we've got the dimensions, let's say this was 6 and 4, then we know that that's 6 and 4. We just need to know that this is, say, 8. Then we can find out the whole surface area. We'd say it is surface area equals 6 by 4 by 2, because there are 2 of these 6 by 4s. Now this is an 8 and this is a 4, so it's a 8 by 4 by 2. That gets me this face and this one here. and then there's just the top and the bottom, which are 6 by 8. So it'd be 6 by 8 by 2. So we'd go 48, 64, and 96, and that would get you 160 or 208 units squared as our surface area. Over here we'd be looking for some information about the height. Right, the height might be 6, and the base might be 5. So we're looking for the area of each triangular end, and then add in these rectangles. So we'd also have to have what the length of that rectangle is. We need to know what this slant height here was, so that we could multiply the 8 by the 4 to get the area of this face here. So we need all this information. Now for the cylinder, the surface area of a cylinder is slightly different. We've got the ends, so if it's a closed cylinder, we've got the 2 pi r squared for the two circles. So our surface area here is 2 pi r squared for the areas of the circles. But this curved surface area here, if you can imagine slicing this can or whatever it is, and then opening it out, and what we'd end up with would be a rectangle. If you can imagine that, anytime you've got a rectangular sheet of paper, you can roll it up and get yourself a cylinder. Now, the dimensions, if you think about rolling this out, the circumference of that circle becomes that length there. So that's 2 pi r, because that's the circumference of a circle. I just lost one note there for a moment. Don't know what happened. Okay, I was just saying that this curved face here, if we cut it and rolled it out and just laid it flat, the net of that particular face. I apologise, one note keeps crashing. Try again. If we slice down the can here, we open out, we lay flat, then this dimension here is this circumference of the circle. Now the circumference of a circle is 2 pi r. So that length there that this rolls out to is 2 pi r. And our this length here is just the height of the cylinder. So that's h. So, and that's just a rectangle. All right, so I've got the two circles, which is 2 pi r squared, and I've got this rectangle that laid flat has dimensions 2 pi r times h. So that's my surface area of a cylinder, 2 pi r squared plus 2 pi r h. Okay, plenty of work to do. That gives us exercise 6c to get on with, and exercise 6d, I believe. 6c and 6d is work on prisms and cylinders, and so we'll get some work requirements for you, and that should keep you busy for a bit. Okay, see you soon.